All right, let's take a look at section 4.1 here. 4.1 is all about exponential functions. So an exponential function is anything where our variable is in the exponent. Right? Now, it is important when we're talking about an exponential function that we say the base, okay, and whatever number is being raised to a power is called the base. The base has to be positive. Okay, if the base is negative, a bunch of funky things can happen. So we have to specify that the base is positive and the base can't equal 1. Okay, because if the base equaled 1, well, 1 to any power we know is just 1. So that would make it very uninteresting. So we have our variables in the exponent, the base is positive, and the base can't equal 1. So let's just start by evaluating some basic exponential functions. All right, so my first one here, I've got 3 to the x minus 2 power. That x minus 2 is in the exponent. So if I want to evaluate f of 5 here, I'm plugging 5 in for x, so that's going to be 3 to the 5 minus 2 power. All right, all that's in the exponent. So that would just become 3 to the third power, which would be 27. Okay. For this one, okay, I want you guys to go ahead and try this one real quick, but make sure you use order of operations when you evaluate here. All right, so if I plug -2 in here, g of -2 will be -2 times 10 to the -2nd power. I need to evaluate exponents before multiplication. So I need to raise 10 to the -2nd power first. So 10 to the -2nd power, if we're thinking about our exponent rules, is the same as 1 over 10 to the positive second. So that would be 1 over 100. So -2 times 1 over 100 would just be -2 over 100, or if we reduce that, -1 over 50. All right. And go ahead and try the last one as well here. So on this one, we're plugging 3.2 in, so we're going to have 4 raised to the 3.2 power. So we're going to need a calculator for that. All right, so let's bust out the calculator. Raise 4 to the 3.2 power. And we get 84.449. Okay, let's round things to 3 decimal places. All right, so 84.449. All right. So next, okay, there's a little space for you to jot down rules of exponents. Okay, these are just basic algebra rules. We touched on some of these a little bit already this year, but I mean, you certainly saw these in Algebra 2 and in Pre-Calc. So if you need to pause the video to get all of these jotted down, please do. I'm going to run through these real quickly, okay, and maybe jot an example down off to the side here. So product rule, okay, if I'm multiplying two things that have the same base, I can add the exponents. For example, if I have x squared times x to the third, I can add the exponents together and say this would be x to the fifth. If I'm dividing two things, right, so if I have x cubed over, if I have x cubed over x squared, I would subtract the exponents. So 3 minus 2 would just get me x to the first power. The power rule, when I'm raising a power to a power, so if I have x squared to the third power, what that's saying is, well, I'm going to take x squared times x squared times x squared, right? So if we're thinking back to our product rule, I can just add these exponents together. Or, okay, the shortcut here is just to multiply these exponents. If I'm raising a power to a power, I can just multiply the exponents together. If I am raising something, a product, to a power, right? So if I've got, well, let me do this. How about if we've got 2x to the third power, right? We need to essentially distribute this power through, right? So this would be 2 to the third power times x to the third power, and 2 to the third power would just be 8, right? So make sure you remember to raise everything to a power, okay, when you're raising a product to a power. Same idea when we have division, okay? If we have 2 over x raised to the third power, I need to raise both the numerator and denominator to the third power. So this would become 2 cubed over x cubed. Okay, and again, this could just be 8 over x cubed. And then the last three, okay, the 0 exponent is just anything raised to the 0 power is equal to 1. The basic idea there is if we have, say, x to the 5th over x to the 5th. Okay, if I think about, well, I want to subtract my exponent, so 5 minus 5 would get me x to the 0 power. Well, we know that anything over itself is equal to 1. So if I have x to the 5th over x to the 5th, that has to equal 1. So that's why we say anything to the 0 power is equal to 1. We talked about this idea a little bit early on as well. Okay, a negative exponent just means I can take that to the denominator. So if I have x to the negative third, that's the same as 1 over x to the positive third. And it works the other way as well. If I have 1 over y to the negative second, well, I can bring that to the numerator and make the exponent positive. So that would be the same as y to the positive second. All right. And then our last exponent rule, whenever we have a fractional exponent, okay, so for example, x to the 3/4 power, if I want to rewrite that in terms of a root, okay, whatever the numerator of my exponent is will be the power inside of the root, and the denominator will be the root itself. So this would be the same as the 4th root of x to the 3rd power. Okay. So again, if you need to pause to get all these jotted down, go ahead and do that real quick. I'm going to move on to the next spot, and we're just going to do a few examples here. Okay, so let's start with something like this. We want to simplify about 6 to the square root of 27 power times 6 to the square root of 12 power. Okay, well, if I am multiplying two things with the same base, I can add the exponents together. So this would just be the same as 6 to the square root of 27 plus square root of 12. Well, to add radicals together, remember, they have to be the same radical on the inside. So what we kind of want to do here is come off to the side and simplify each of these radicals. So the square root of 27, well, the largest perfect square that goes into that would be 9, right? So I could split this up into the square root of 9 times the square root of 3. So this would become 3 times the square root of 3. And then square root of 12, the largest perfect square that goes into that is 4. So I can make this the square root of 4 times the square root of 3. And then the square root of 4 is 2. So I can rewrite this as 6 to the 3 radical 3 plus 2 radical 3. Well, now I can add these together since I have the exact same thing inside of the radical. I can make this 6 to the 5 radical 3. Well, now I could actually simplify this a little bit further. Okay, I could split this up into 6 to the 5th power, then to the square root of 3. So I can evaluate 6 to the 5th power, and that's a nice number. That's actually 7,776. So then that would be raised to the square root of 3 power. Okay, so when we're using rules of exponents to simplify. We want to combine as many things as possible, and then also, if we can raise something to a nice power to make it look a little nicer, we want to do that as well. Okay, so let's try another one here. Do this in red. About 6 to the square root of 3 power to the square root of 3 power. Okay, I'll give you guys a minute to try this one. All right, well, when we're raising a power to a power, I can multiply the powers. So the square root of 3 times the square root of 3 is just 3, right? So 6 to the third power is just 216. All right, so hopefully that one was pretty straightforward. How about, let's do one more example here. How about 3 to the square root of 8 times 3 to the square root of 2. All right, give this one a try. All right, so here we can add the exponents together. So this would become 3 to the square root of 8 plus the square root of 2. Now remember, to simplify something like this, we have to have the same thing on the inside of the radical. So I can come over here and try to simplify the square root of 8. Well, I can split that up into the square root of 4 and the square root of 2. So that would become 2 radical 2. So I can come back over here and say this would be 3 to the 2 radical 2 plus 1 times radical 2. So this would be, if I add these radical 2's together, I would end up with 3 radical 2's. And then I can do 3 to the third power, right? I can essentially split this up like this and do 3 to the third power, which would be 27. And then that will be raised to the square root of 2 power. All right. Let's do one more example. How about something like this? About 5 to the radical 3 power times 25 to the radical 3 power. Okay, so here my bases are different. Remember, everything we've talked about said the bases have to be the same. Well, I can rewrite 25 so that it has a base of 5. Right? I can change this into 5 to the square root of 3 times, I can rewrite 25 as 5 to the second power. Right? Then that would still be raised to the square root of 3. So this would just be the same as 5 radical 3 times 5 to the 2 radical 3 power, right? So now I can add the exponents together and make this 5 to the radical 3 plus 2 radical 3. If I add the exponents then, that'll just be 3 radical 3, and then I could raise 5 to the third power. Okay, remember that's essentially just splitting this up like this. So 5 to the third power is 125, so we can say 125 to the square root of 3. All right. So the next thing then is to talk about graphing exponential functions. So let's start by just getting a table of values to graph y equals 2 to the x. Okay, so x and y. So I don't know, let's start with -3. So if I plug -3 in here, 2 to the negative third power, okay, well, that would be the same as 1 over 2 to the positive third, which would be 1/8. So -3, 1/8 would be right there. Then if I plug in -2, 2 to the negative second will be 1 over 2 to the positive second, which would be 1/4. If I plug in -1, 2 to the negative first would be 1 over 2 to the first, so 1/2. If I plug in 0, 2 to the 0 power is just going to be 1. If I plug in 1, 2 to the first is 2. If I plug in 2, 2 squared is 4. So we're growing pretty quick here. And then if I plug in 3, 2 to the third power is 8. So we can see that this graph is going to grow pretty quickly. Okay, so this is what the graph of an exponential function is going to look like. Okay, now we'll talk about some of the important characteristics here in a minute, but notice if we think about if we started plugging in really large or really small numbers, right, kept going further and further into the negatives, we could never reach 0, right? We would just keep getting 1 over a larger and larger number in the denominator. So y equals 0 actually ends up being a horizontal asymptote here. Another interesting feature, as long as there are no shifts or anything to the graph, whatever my base is, when I raise that to the 0 power, I get 1. So the y-intercept, okay, again, as long as we haven't shifted the graph at all, right? There's no plus a number out here or anything like that. Oops. The y-intercept will always be 1. Okay, so let's take a look at another one. Let's do 1/2 to the x power, and let's plug in those same values. So if I plug in -3, 1/2 to the -3rd power. Okay, well, this would be the same as 1 to the -3rd over 2 to the -3rd, right? Which would actually end up being the same as 2 to the 3rd power, right? Remember, if we have a negative in the denominator, I could bring that to the numerator. So this would actually be 8. So -3, 8 is on the graph here. If I plug in -2, that'll be 1/2 to the -2nd power. So same idea. I'll have 2 to the -2nd in the denominator. So I can take that up to the numerator, and that would end up being 4. If I plug in -1, 1/2 to the -1st, it's going to be 2. If I plug in 0, 1/2 to the 0 power is still 1. Anything to the 0 power is 1. If I plug in 1, 1/2 to the first is obviously 1/2. If I plug in 2, 1/2 to the 2nd power. Remember, we said the numerator and denominator would both be raised to the 2nd, so it would be 1 to the 2nd over 2 to the 2nd, which would be 1/4. And then if we do 3, same idea. 1/2 to the 3rd will be 1 cubed over 2 cubed, which would be 1 over 8. So this graph is actually just the mirror image of what we just did, okay, reflected across the y-axis. So y equals 2 to the x was an exponential growth function, and y equals 1/2 to the x was an exponential decay function. Okay, and we'll look at these properties here on the next slide. All right. But if the base is less than 1, that tells us that the function is going to decrease. If the base is greater than 1, our function is going to increase. Okay, so let's take a look at that list of properties. So again, here, if you want to pause the video and get these all jotted down, more than welcome to. I'm going to talk about each of these real quick here. So again, we're talking about an exponential function where the base is greater than 0. Oops, that should actually say a cannot equal 1. Right? The base is greater than 0 and the base cannot equal 1. Now, I already mentioned, some of these properties are different if the graph is shifted. For example, if we had, a to the x plus 2 or something like that, that would shift the graph up 2 spaces. So all of these properties assume that we haven't shifted our basic exponential function. the domain of any exponential function is all real numbers. Okay, the range, we said y equals 0 was an asymptote, so that means the range is 0, not including 0, all the way up to infinity. And then I mentioned this for our last two graphs as well. When our base is greater than 1, our function is increasing, and when the base is between 0 and 1, okay, it's decreasing on its entire domain. Another interesting fact, which we will look into a lot this chapter, is exponential functions are one-to-one, which means they have inverses. Okay? The inverse of an exponential function is logarithm, and we'll get into that in the next couple of sections. We'll explore the relationship between exponentials and logs. Since y equals 0 is an asymptote, that means that the graph never crosses the x-axis, right? So it has no x-intercepts. There are three interesting points on the graph: -1 and 1 over whatever the base is. Like I said, the y-intercept is always 1, again, unless we've shifted the graph somehow. And then the point 1 and the base will always be on the graph. Y equals 0 is a horizontal asymptote, and the graph of y equals a to the negative x is a reflection over the y-axis of the graph of y equals a to the x. This last statement is actually talking about the graphs that we just did. Okay, so the first one we graphed was y equals 2 to the x, right? The second one we graphed was y equals 1/2 to the x power. Well, another way of writing 1/2 would actually be 2 to the negative first power, right? 2 to the negative first is the same as 1/2. So 1/2 to the x would actually be the exact same thing as 2 to the negative x. So that's where we're getting this last fact from. Okay? Y equals a to the negative x is a reflection across the y-axis of the graph of y equals a to the x. Okay? So again, if you need, pause the video and jot these properties down. So let's take a look at a few graphs here. So for these, I think in the notes it says we can use Desmos to graph. But I'm just going to plug in a few values to get our picture. So 5 to the negative x, well, if I plug in 0, I know I'm going to get 1, so that's an easy place to start. Well, if I plug in 1, 5 to the negative first is going to be 1 over 5. So that'll be down here already, right? Now if I plug in -1, 5 to the negative first power would be 5 to the first power. So that's going to be 5. If I plug in -2, well, 5 to the negative second would be 5 to the second, which would be 25, which would be way up here. So this graph actually ends up looking something like this, right? It's a very steep exponential decay function, right? So this, we could say this graph is the reflection of y equals 5 to the positive x. That would be one way to describe the position of this graph. And I guess we do want to think about that, right? In terms of, we talked about transformations of graphs in the second chapter. So if we're starting at y equals 5 to the x, the only thing I have to do here is make the exponent negative, so that would be take this graph and reflect across the y-axis. Okay, for the next one, y equals -3 to the x. Okay, now that negative, okay, isn't inside of parentheses, so we're not saying the base is -3. We're essentially saying this, right? That negative sign is out in front. So we can say that we would raise the value, or raise 3 to whatever value we're plugging in, and then multiply it by -1, essentially. So if I plug in 1, well, 3 to the first power is 3, times -1 would be -3. right? So like down here. If I plug in 0, well, 3 to the 0 is 1, times negative would be -1. If I plug in -1, 3 to the negative first power would be 1 over 3 to the first, then times -1, so that would be -1/3. So we end up seeing that our graph is going to do something like this. All right. If you remember back to our transformations chapter, or transformations section, if we had a negative out in front, that reflects our graph across the x-axis. So if we're starting with the graph of y equals 3 to the x, and I throw a negative sign out front, I'm just going to reflect that across the x-axis. Okay. Now, our last one, we've got a couple of things going on here. So let's plug in a few values and see what happens. So if I plug in 0, that's a good place to start, right? Well, I'll have 4 to the negative third power plus 1. Right? So 4 to the negative third power would be 1 over 64 plus 1. Right? So that's going to be something like, right there, like 1 and 1/64. Well, what if I plug in 1? Right, so 4 to the negative second power plus 1, well, that's going to be 1/16 plus 1, so that's still just barely above 1. What if I plug in 2? I'll have 4 to the negative first, which would be 1/4 plus 1, so that would be 1 1/4. If I plug in 3, 4 to the 3 minus 3 is 0, so 4 to the 0 is 1, plus 1 would be 2. If I plug in 4, 4 to the 4 minus 3 would be 4 to the first, plus 1 would be 5. Okay, so we end up getting something that looks like this. Okay, so this graph is shifted some. Okay, now we can talk about, again, if we start with y equals 4 to the x power, and I want to shift it. Well, we talked about using order of operations, so what's happening in the exponent will come first. And this is, we've talked about, whenever we're adding or subtracting something to x inside of the function, that's a shift left or right. If I'm subtracting, that's going to be a shift to the right 3. So I'm going to take this graph and move it right 3, and then outside of the function, that's going to tell me to go up 1. So if I took the graph of y equals 4 to the x, okay, and shifted it right 3, up 1, this is where I would end up. All right. So again, so to graph exponential functions, okay, we can think about either making a table, which we could do for any function, but it might be a little quicker if we think about our transformation section. All right. So the last part here, okay, is finding an exponential function that goes through certain points. Okay, so it's going to be in this form: y equals some number times a to the x. We're given 2 points. So what we want to do is just start by plugging in one of those points. So plug 1 in for x and 12 in for y and see what happens. So I guess I can write out the y equals c times a to the x. So I'm plugging in 12 for y and 1 for x. Okay, so now I just have 12 equals c times a, right? So I want to solve this for one of the variables. All right, so if I mean, it doesn't matter which one. Let's solve it for c. So if I divide both sides by a, I would have 12 over a equals c. Okay, well, let's do the same thing with this point. Okay, let's plug in 3 for x and 108 for y. Okay, so 108 equals c times a to the third power. All right, so what we can actually do now, okay, we can take what we solved for c here and plug this in for c over here. Okay, so I'm going to change this to 108 equals 12 over a times a to the third power. And I'm just going to solve for a now. So 108 equals, so 12 over a times a to the third. Well, a to the third over a to the first would be a to the second. Then I can divide both sides by 12. And that'll be 9. So take the square root of both sides, and we would technically get plus or minus 3, but a is the base, right? So we said the base has to be positive. So we get that a is equal to 3. So now, to finish this out, okay, we ultimately need to solve for c, right? So to finish this out, I'm going to take this value of 3 and plug it into the simplest equation here to solve for c. So we've got 12 equals c times a. So I'm plugging 3 in for a now. So 12 equals c times 3. Divide both sides by 3. And I would get that c is equal to 4. All right, so what we've come up with now, okay, we needed to solve for a and to solve for c. So my final answer would be y equals 4 times 3 to the x. Okay, this is the exponential function that will go through these 2 points. Okay, so there's a little bit going on there. Okay, there'll be a couple of homework problems where I want you to try something like that. So you're going to end up plugging both of these points into the function separately to solve for a and c. All right. So the second part of this lesson then is about interest. So just real quick, okay, percentage increase or decrease. Say if I had $100, right? And I say, well, over the next year, my $100 increased by 12%. Okay, well, what I would do to calculate that would be to say, well, my new total is going to be my old total plus 0.12, right? 12% as a decimal is 0.12 times that principal amount. So 100 plus 0.12 times 100 would be 12. Right? In this example, that's pretty easy to calculate. So $100 plus a 12% increase would be $112. Now, a decrease, we would just be subtracting, right? So let's say I start with a not as nice amount. Let's say I start with $156, and over this year that I'm talking about, my investments decrease, right? They go down by 6%. Well, if I'm talking about a decrease, I'm going to subtract, right? So I'm going to subtract, if I'm doing 6%, that would be 0.06, right? Make sure you're not making it 0.6 if we're talking about 6%. 0.6 would be 60%. So 0.06 times what I started with. So let's see. Might need the calculator for that. So 0.06 times 156, $9.36. So 156 minus 936 is going to be 146 and 64 cents. Okay, so that's just real quick, the basic idea of percentage increase and decrease. So we're actually going to skip this example here. It says we're going to do page 441, number 99, but we're going to skip that example and just go into our interest formulas. Okay, so simple interest, okay, is the idea, okay, that interest is charged just on the amount borrowed. All right, so interest, okay, simple interest, okay, we say interest is equal to, P stands for principal. So principal means the amount that you invest. R stands for rate, and T stands for time. Okay, so the amount of interest is the principal amount times the rate times the time. This formula, simple interest, is assuming that you do not earn interest on the interest. Simple interest is when you only earn interest on an amount that you invest. So, for example, if we invest $1,000 and our simple interest return is 7% per year. Okay, so first, an equation to represent this situation, okay, plugging our information in here, we can say our interest is equal to the principal amount, which is 1,000, times the rate, so 7% as a decimal would be 0.07, times the time. Right? We don't have any information on the time yet. Well, so B and C ask us then to use this formula. So find out how much interest we've earned after 1 year. So interest will be 1,000 times 0.07, and then time is 1. Right? We're saying after 1 year. So 1,000 times 0.07 is 70. Right? So after 1 year, made $70 in interest. Well, same idea after 5 years. Simple interest will be principal amount times 0.07 now times 5 years. So that will end up being 350. So then the last part just says, well, how much has he actually, or does he actually have in his account now after 5 years? So to do that, we would say, well, we're going to take what he started with, the principal, which was 1,000, plus how much interest he has accrued. So after 5 years, Alex has $1,350 in his account. All right. So simple interest isn't usually how the world works. Okay? Usually, we talk about compound interest. Compound interest is when you earn money on the interest. Okay, you gain interest on the interest. The compound interest formula looks like this. A equals P times 1 plus R over N to the NT power. Okay, now, just like before, P is principal, and that means the amount of money that we started with. R is still the rate. Now, N actually shows up twice in this formula, right? N is here, and N shows up here. N is the number of times we are compounding per year. Okay, and I'll explain what that means in a second. Times compounding per year. And then T is number of years. right? So if $2,200 is deposited in a bank that pays 5% annual interest, find the future value after 1 year if the interest is compounded semi-annually and daily. Okay, so from this problem, we have all the information that we need to plug into our formula. Okay, so first, let's try to collect all this information. So our principal amount is what we're starting with, that $2,200. Then times 1 plus the rate goes in the numerator here. So 5% as a decimal is 0.05 over n, the number of times compounded per year. Okay, well we get this, semi-annually. Semi-annually, okay, semi means twice a year, right? So the number of times compounded per year is going to be 2. So that goes in the denominator here, and then that also goes in the exponent here. And then our last value that we need is t. That's the number of years. And they tell us that this is just going to be after 1 year. So my exponent is going to be 2 times 1. All right, so let's see, we're going to have 2,200 times 1 plus 0.05 over 2 raised to the second, or 2 times 1 power. So this is not the amount of interest, this is the final amount in the account. So 2,311,375. Now, since we're talking about money, we'll round to the nearest cent. So 375, we would round to 38 cents. So I guess I should have specified up here that A is the final amount. Okay, it's different than our last formula, right? In our simple interest formula, the I over here was just the interest. In our compound interest formula, this value is the final amount. So let's do the same thing then for if we compound our interest daily. So that'll be 2,200 times 1 plus the rate stays the same, so 0.05 over, now daily, so that's number of times per year. There are 365 days in a year, right? So we would divide this by 365, then raise that to the 365th times 1 power. So let's calculate that. So 2,200 times 1 plus 0.05 divided by 365 raised to the 365th power. So we get an extra dollar and change, right? Compared to if they compound the interest twice a year or 365 times a year. So it actually ends up not being that much more money, right? So 2312.79, 2312.79 cents. All right. So the last idea then is continuously compounding. Okay, so if we think about this formula, okay, and we say, well, I want to make this n infinity, basically. I want to compound this interest as many times as possible. Right? So I mean, we could say, well, I want to do this every minute or every second or every millisecond. I want to compound the interest. Well, what we say is we're compounding continuously then. And what happens, okay, we actually get a very special number out of this idea. So our formula is still going to be A equals the principal amount. But then in the parentheses here, if we say, well, n is basically going to infinity, what happens is we get some number called E, okay? So A equals the principal amount times this special number E raised to the rate times time power. So those other pieces stay the same, right? P is the principal amount. R is the rate. And T is the number of years. But E is some special number. Now there's actually an E button on your calculator. Okay, if you, it's actually in two places. It's right above the division sign. So if you hit second division, that'll give you the number E, or it's actually above the natural log down here, the ln. So you could, if you wanted to raise E to a power, it'll automatically give you E with an exponent then down here. So the number E, okay, the number E is kind of a weird idea, right? But essentially, if I were to take this formula, this 1 plus, and if we just make the rate 1, and I keep making these numbers, these n values, larger and larger. Okay, so I mean, if I made these 1,000,000 or 10,000,000 or 10 billion, okay, so we can say this, okay, for this, as n approaches infinity, or as n gets larger and larger and larger, this approaches the value of E. So as n goes to infinity, this approaches E. So a problem could be something like find the amount when a principal of $8,300 is invested at a 7.5% annual interest rate, compounded continuously for 8 years and 3 months. Okay, so let's try to unpack what's going on here. So to plug these values into the formula, the principal amount is $8,300 times E, the number E, raised to the rate, so 0.075 is my rate, 0.075 times the time, so time is the number of years, so 8 years and 3 months. How would I write 8 years and 3 months as a decimal? Okay, well, 3 months would be 3/12 of a year, right? So 3 months we can think of as 3/12, which if I divide 3 divided by 12, that's the same as 0.25. So 8 years and 3 months we can say is the same as 8.25 years. So if I plug all of that into my calculator, let's see, 8,300 times E, and I'm going to go ahead and use this one since we're raising E to a power. So times E to the 0.075 times 8.25. That's my exponent. So P times E to the R times T power gets me 15,409.83 cents. So 15,409.83. All right, so compounding continuously, okay, essentially saying we're going to take this formula and make n go to infinity. We come up with this number E, right? So the last thing that we want to do then is to figure out what E is, okay? So if I graph f of x equals e to the x, we can see the value of E, all right? So let's get Desmos up here, and let's say I graph e to the x power. Oops, e to the x power. There we go. So e to the x power, we know from our properties of graphs of exponential functions that we just talked about, the value 1, then whatever the base is, will be on the graph. So this tells me the value of E is 2.718. All right? Now, you can actually take it out to a few more decimal places. The value of E is 2.718281828. So it kind of looks like it's going to repeat, but then it's 459. All right. So this E is going to be very useful throughout this whole chapter. Okay. I know that was a long lesson. I apologize for the length. The homework is actually on the bottom of your paper if you want to get started, but we will have all day in class on Wednesday to work on the homework.